energy balance is what we have discussed yesterday. So yesterday we have solved two problems. So what are the two problems? So two problems we have solved. But what is the two problems is adiabatic reactors. Adiabatic reactors. So for adiabatic reactors, what do we learn is basis doesn't matter. Whatever it may be the inlet for it, it doesn't matter for the adiabatic reactors. So because the number on the left hand side and the right hand side basically will cancel out. So we'll write another problem. So write this problem. The reaction A gives B. Write this problem. The reaction A gives B is conducted in an adiabatic plug flow reactor. In an adiabatic plug flow reactor. Brackets PFR. PFR. Pure A at a concentration of pure A at a concentration of pure A at a concentration of 2 kilomole per meter cube is fed to the reactor at the rate of 0.01 meter cube per second and at a temperature of 500 Kelvin. If the exit conversion is 20%, then the exit temperature is given data delta HR equal to minus 50,000 kilojoules per kilomole. Cp of A equal to Cp of B equal to 100 kilojoule per kilomole Kelvin. So this is the given data. So what is the biggest difference between previous problems and these problems? That I would ask you to, let's say, study carefully. All these properties are not a functions of temperature. This is by default. Even if it is not given, you can consider that. PF or CSTR doesn't matter because energy balance will be same. Yes, units of specific heat. CP units are different and CP of A and CP of B given differently. Now, this information is not required. This particular information has no meaning. Has no meaning. Without this also you can solve the problem here. Because for adiabatic reactor basis doesn't matter. Try to solve it. So let's start. So how do you? So here first you should write, let's say, mole balance. I think without mole balance also you will get it, but mole balance we should write because Cp of A and B are given. So we can't write, let's say, overall. So if I take the reactor, what goes in is Fa naught, what comes out is Fa and Ft. What is Fa naught? Ca naught into V naught. What is Ca naught? F is Ca naught into V naught. What is Ca naught is 2. What is V naught is 0.01. So 0.02 kilomole per second. So what is conversion? 20% conversion. Can you calculate Fa and Fb? So what is Fa is 0.016 kilomole per second. What is Fp is 0.04 kilomole per second. Why I am writing A and B separately? Because Cp of A and Cp of B are given. This problem doesn't matter because Cp of A, Cp of B are same. But if the problem Cp of A, Cp of B is given differently, then you will face problem. Heat enthalpy of reaction. This is 0.004. What is Fa? Fa naught into 1 minus Xa, no? Unconverted. What is Fb? Fa naught into Xa. Now, what is heat in? How do you calculate heat in is 0.02 into Cp of A into temperature of in is 500 minus T reference. What is heat out? Heat out will be two components, A component and B component. 0.016 into Cp of A into T out minus T reference plus 0.004 into Cp of B into T out minus T reference. So this is what is heat out. M is not there. No, here it is Cp of A multiplied by molar flow rate because Cp is based on moles. So your M is molar flow rate now. Plus what is delta HR? What is delta HR? Minus 50,000 into Fa naught into Xa. What is FA naught is 0.02. What is XA is 0.2. So this is what is so this is one term. This is second term. This is third term. Substitute all the values and get what is T out. This is how you should solve when you have here CP is based on moles. This is slightly tough problem. Here CP is based on moles. So answer is CP is based on moles. So I always see only 5-10 people are only replying early. 600 Kelvin, correct? So if somebody has not attended the yesterday's class, this class will be slightly difficult, not very difficult. So if you have any doubts, please let me know in the charts or let's say when we are meeting next time. Clear? I see always 5-10 people only, let's say, replies in the class, let's say out of the entire session. So everybody understood why I have written the balance like this here is very important. Yesterday, if you see, I have written just, see, mass-based energy balance is always extremely simple because MCP delta T is equal to MCP delta T. Clear? So here, when CP is given in terms of moles, then the problem begins. So if everybody done, the answer is 600 Kelvin. Why we have written FA naught into XA? Because FA naught into XA is moles of A entered multiplied by XA. No? See, I have these many moles of A entered. Out of this one, 80% is unconverted, 20% is converted. So why I am writing A and B separately? Because CP of A and CP of B is given directly. Yesterday, why we didn't write the balance? Because CP is given with respect to mass. And CP of A and B are not given different directly, no? So I think I'm getting a lot of doubts. So meaning that So I need to give some more time for you to understand. If CP value is different, then actually generally CP values will be same. I have another problem where CPs are different. So I'm going to derive a small shortcut here. So what is the shortcut is FA naught into CPA into T in minus T reference, which is equal to FA into CPA into T out minus T reference plus FP into CPB into T out minus T reference plus delta HR into FA naught into XC. This is what is written or not for this problem. Remember, this problem is applicable for this problem only. For this problem only, this shortcut. You can't apply, let's say, universally this one. Now, in this problem, Cp of A equal to Cp of B, which is equal to, let's say, Cp. For this problem, Fa naught equal to Fa plus Fb also. Why this is? Moles in equal to moles out because the reaction is simple. A gives B. Because the reaction is simple, A gives B. Because it is equimolar reaction. That means moles doesn't increase. Moles doesn't increase. So clear? Then applying these two rules, then what happens here is Fa naught into Cp into T in minus T reference is equal to, if I combine these two, then what happens? Fa plus Fb into Cpa. So Fa plus Fb into CPA into T out minus T reference plus delta HR into Fa naught into Xa. But what is Fa naught into plus Fa naught? No. Then this Fa naught here, and Fa naught here will cancel on both sides. Then what happens you will get is Cp is equal to T in minus T out is equal to delta HR into Xa. So this is the equation. So if I rearrange the terms, T out minus T in, which is called as delta T, equal to minus delta HR XA divided by Cp. This is what is the famous equation that you see in Levin's pill. Delta T equal to delta HR minus delta HR into XA by Cp. Why minus here? Because T in minus T out, I am writing it as T out minus T in. This is the shortcut, but this shortcut is applicable for this problem. That means this should be one condition and it should be an equimolar reaction. You cannot apply this shortcut universally. So just spend 1 or 2 minutes. So the T reference generally will cancel on both sides. That is how CP and CPB are given. So I'll show you next problem where CPs are different, but T reference will cancel. So we'll go to another problem. Yes, if I'll next problem will be slightly tough, but it is so write this problem. Write this problem. The homogeneous reaction A plus B gives C. A plus B gives C is conducted in an adiabatic CSTR at 800 Kelvin. At 800 Kelvin. To achieve 30% conversion of A. To achieve 30% conversion of A. If the feed, a mixture of A and B, if the feed, a mixture of A and B is available at 550 Kelvin, then mole fraction of A, in the feed, that is consistent with the above data is given data Cp of B 100 joule per mole Kelvin, Cp of A 50 joule per mole Kelvin, Cp of C 150 joule per mole Kelvin, delta HR minus 100 kilojoule per mole, This is one of the toughest problems in the gate. One of the tough problems in the gate. Because this is energy balance and non-equimolar. Can you apply the previous formula here? You can't, because basically moles are not same. Moles in is not equal to moles out. Answer is 5/7. So I'm giving some time so that you will get practice actually. If I solve and you will note down, you may not get. How do you start this problem? First start, let's say 100 moles of feed. You start with, let's say, 100 moles of feed. And out of 100 moles, let's assume that Y is moles of A, then what is rest? 100 minus Y is B. First establish the mole balance. Once you establish the mole balance, the next is simple. Write energy balance. Establish the mole balance. Let's start solving together. So how do you take the basis? 100 moles of feed. Out of Y is, let's say, A. 100 minus Y is, let's say, B. Clear? Now, conversion of A is 30%. So what does that mean? Conversion of B is also 30%, or conversion of A is 30%. Can you take conversion of B also as 30%? No, we don't know basically. If the feed is in the stoichiometric ratio, then only conversions are equal. CRE, we have solved some of the problems initially. So basically we don't know. So how do you write mole balance? Then here, how do you write mole balance is 100. How do you write mole balance is 100 feed out of Y is A, 100 minus Y is B. So what is the reaction taking place? A plus B gives C. How many moles of A reacted? 0.3 into Y. How many moles of B reacted? 0.3 into Y. How many moles of C formed? 0.3 into Y. Everybody agrees 0.3 into Y moles of A reacts with 0.3 into Y moles of B, forms 0.3 into Y moles of C. Then what is left? A is Y minus 0.3 Y. What is B left? 100 minus Y minus 0.3 Y. What is C formed? 0.3 into Y. So this is A, this is B, this is C. Understand here only. This is the key for the problem. If you are done here, then next thing is simple. No, take these components and write the energy balance. somebody will do a mistake here. Somebody will do a mistake. They will write it as 100 minus y into 0.7, assuming that 100 minus y is my feed and 0.3 is converted, then 100 minus y into 0.7. That is wrong. We don't know what is the conversion of B. But still we can solve the problem, because if you know how much A converted, you know how much B converted, how much C formed. What is B into the reactor minus what is B reacted? What is A into the reactor? What is A reactor? This is what is A in. This is what is A reaction. This is what is B in. This is what is B reaction. Everybody done till now? Is everybody clear till now? Because why we are taking 0.3 y? Because 30% of A is converted now. Then I am going to next board. So I'll rewrite the energy balance again. Y of A 100 minus y of B, 0.7 y of A, B is 100 minus 1.3 y of B, C is 0.3 y. So this is what is A, B, C. Now how do you write the energy balance? What is energy balance? Y into Cp of y into what is temperature of the inlet? 550 minus T reference. Now inlet has two components. So 100 minus y into Cp of B into 550 minus T reference, which is equal to 0.7 into y Cp of A into what is T outlet? T outlet or CST temperature both will be same, no? 800 minus T reference plus 100 minus 1.3 y into Cp of B into 800 minus T reference plus 0.3 of y into Cp of C 800 minus T reference plus delta HR. What is the delta HR given? Minus 100 kilojoules. Now minus 100 into 10 power 3. Is this with respect to A or B? Doesn't matter, because A reacted, both B reacted will be, how many moles of A reacted will be into 0.3 into Y. So basically right here, this is one combination. This is what is heat out. This is what is enthalpy in, enthalpy out plus enthalpy of reaction. So any doubts here? Take time, slowly. If you realize I'm solving these problems extremely slow manner, reason because I want you to put enough brain into the problems while solving, because this is too delicate problems, meaning even if you have done a small mistake here, then you will not, suppose simple mistake here will not cancel T reference on both sides. If you see today almost 1 hour class, we have solved only 2 problems, because doesn't mean that in gate also you will spend half an hour. The first understanding should be very good, so that when you understand the problem perfectly, then you will solve the problems in a faster manner. So I will take some more doubts. So because moles of air, you have to take only one reactant. So I will not take, let's say, delta HR multiplied by moles of A reactor plus moles of B reactor. No, delta HR will be expressed always with one of the reactants. Y minus 0.3Y is nothing but 0.7Y. No, somebody is asking why Y minus 0.3Y. Y minus 0.3Y is what? 0.7Y. No. You don't need to deal with D reference. T reference will always cancel. If T reference doesn't cancel on both sides, then there is a mistake in the data of the problem. So how did I write 0.7 here? Because this is Y minus 0.3 is nothing but 0.7. No? You will get exactly 5 by 7. 10 by 7 somebody got. 10 by 7 will not be the answer, no? Because mole fraction should be less than 1. 10 by 17. Cp values in joules, joule per mole Kelvin. So are you getting 10 by 17? Just check once again. Then I have changed the data, so maybe 10 by 17 might be right. Did everybody solve this one? So we'll go to, till now whatever we have solved is the adiabatic reactor. So next problem what we are going to solve is what is non-adiabatic reactors. We'll solve one problem in the model of non-adiabatic reactors. Write this problem. Why is something you need to find out. For why, what value should take is somebody's question. A CSTR is to be designed. A CSTR is to be designed in which an exothermic liquid phase first order reaction of the type A gives R is taking place. A gives R is taking place. The reactor is to be provided. The reactor is to be provided with a jacket. The reactor is to be provided with a jacket in which coolant is flowing. Following data is given. Ca naught 5 kilomole per meter cube. Conversion of A 0.5. Feed temperature 40 degrees centigrade. Feed temperature 40 degrees centigrade. Rate constant at 40 degrees. 1 minute inverse. Delta HR minus 40 kilojoule per mole. Delta HR minus 40 kilojoule per mole. Density 1000 kg per meter cube. CP 4 joules per gram degree centigrade. 4 joules per gram degree centigrade. Volumetric flow rate 10 power minus 3 meter cube per minute. 10 power minus 3 meter cube per minute. Bracket some information is given, not I no need to write or write. Rho and Cp are same for reactant and product streams. Rho and Cp are same for reactant and product streams. First question. If the reactor temperature is 40 degrees centigrade, if the reactor temperature is 40 degrees centigrade, then amount of heat removed in kilowatts is second question. If the reactor temperature is 50 degrees centigrade, then the amount of heat removed in kilowatts is. So these are two problems. What is heat of reaction given is minus 40 kilojoule per mole. So I'll state a CSTR is to be designed in which exothermic liquid phase reaction of the type A gives R is taking place. The reactor is to be provided with a jacket in which coolant is flowing. Ca0 is 5 kilomole per meter cube, Xa is 0.5, feed temperature is 40 degrees centigrade, rate constant 1 minute inverse, density 1000 kg per meter cube, Cp 4 joule per gram degree centigrade, delta HR minus 40 kilojoule per mole, volumetric flow rate is 10 power minus 3 meter cube per minute. Clear? So basically it is a CSTR A gives B is taking place. It is non-adiabatic reactor. So what is given is Ca0 equal to 4 kilomole per meter cube. Conversion of A is 0.5. Temperature of feed is 40 degrees centigrade. Rate constant 1 minute inverse. Rate constant information is not relevant here. Just given but has no use. 1 minute inverse. Delta HR minus 40 kilojoule per mole, density 1000 kg per meter cube, Cp 4 joules per gram degree centigrade, V0 is what is first question is if temperature of reactor is 40 degrees then what is Q in kilowatts. Second question is temperature of reactor is 50 degrees, what is Q in kilowatts. Here Cp is based on mass. Here basis is important. Remember here basis is important. Your answer depends upon basis. You can't say non-adiabatic reactors doesn't depend upon the basis. They are dependent on the basis. So I'll give 5 minutes time. Just try to write the equation. Basis is not required. No, basis is already given. Why do we take basis here? If reactor temperature is 40, that means outlet temperature is also 40. No? So first one is 5/3 answer. Somebody who is saying kilowatts, 100 kilowatts. See, remember, see the units of V naught. It is meter cube per minute. So the answer that you are getting is kilojoules per minute. So divided by 60. You have to convert kilojoules by second. The second one is 1 kilowatt. So let's start writing the energy balance. So here basis is important. You can't say that basis is doesn't matter here. So what is given is 10 power minus 3 meter cube per minute. So this will translate to how many kg per minute? Into 1000. So this will be 1 kg per minute into density. Clear? So now what is energy balance is enthalpy in equal to enthalpy out plus heat removed plus enthalpy of reaction plus Q plus heat of reaction. What is heat in is mCp delta T 1 into what is Cp is 4 joule per gram degree centigrade. So convert to joule per kg. So 4000 into what is reactor temperature is 40 minus T reference. Clear? So this is kg per minute. This is joule per kg degree centigrade. This is degree centigrade. So overall, combinedly, what you get unit is joule per minute. which is equal to what is heat out? 1 into 4000 into T out minus T reference plus Q plus what is heat of reaction? What is heat of reaction given? Minus 40 kilojoule per mole. Minus 40 into 10 Q joule per mole into FA naught into XA. What is FA naught? What is FA naught is 10 power minus 3 meter cube per minute into what is CA naught is 4000. What is XA is 0.5. So what is first question is, if T out is, what is first question is, if this T out is 40 degrees centigrade, then what happens? This will cancel. So let's say this and this term will cancel. So what do you get as Q is 40 into 10 Q into 10 power minus 3 into 4000, which is what is FA naught into 0.5. So this and this will cancel, but what you are getting is joule per minute. Then this is 40 into 4000 into 0.5 divided by 1000 divided by 60. So this will become kilojoule per second. Correct or not? CA naught is 5000, no? Sorry. So this will become 5 by 3 kilowatts. What is next question? Just replace this to 50 degrees centigrade. But remember here units are joule per minute you are getting, but you need to convert kilowatts. Because this why MCP not R is not used, because this 1 kg is combined flow rate. No need to use A and B, no. CP is combined CP. So everybody got 5/3, and second one you will get 1 kilowatt. I think we will stop it here. So with this one, entire CRE is completed except the new topics which are added, which is kinetics of enzymatic reactions and how the catalyst deactivation, that we will discuss tomorrow. So with tomorrow, CRE syllabus will be completed. And so basically, and maybe Thursday, Friday I spent for the problems. So with the Friday, so basically CRE will be completed. So if you have any doubts, please clear in this next 2 or 3 sections. So once the CRE is completed, I'll share that MSUBU copy, or maybe in between also, so that you can solve MSUBU problems also. If you have any doubts, then I can clear your doubts. In both the cases, T reference will cancel. Somebody is saying in second case, T reference will not cancel. Why? T reference has same, no? 4,000, 4,000. T reference will cancel in both sides. Any doubts you have? Because you are removing the heat, no? What is second answer is 1 kilowatts. Use of jacket with coolant in this question, that is what is heat removed. Negative order reaction means we can write K by Ca or Kca power minus 1, which are same, no? Negative order is K by Ca square, all this. So any other doubts? For the previous sum, what was the final answer? What is previous sum? 10 by 17. If it is, see, first order reaction means Kca. First order negative means K by Ca. First order means Kca. Negative order means K by Ca. Negative minus 1, you can't call it as a first order. Kca power minus 1, you can't call it as a first order. So, when Cp is based on moles, then the basis is important, else doesn't depend upon S. When Cp is based on moles, you have to be extremely careful. Then you have to see whether Cp is given as component wise or let's say individually, then you have to see. If it's Cp is based on mass, then problems will be easy because mass flow rate doesn't change. Simple concept, mass doesn't change across the reactor, but moles will change across the reactor. So can you show how 1 kilowatt is coming? See, this is what, no. In this question, replace this with 50. Replace this with 50, 40 with 50. Then this will not cancel. Then what is left is 4,000 Q is equal to, along this 5 by 3 minus 4,000 minus 10. That is what is remaining. So it is simple mathematical term. 40 is replaced with 50 and everything will come in terms of joule per minute. So you have to convert into joule per second, kilojoule per second. So any other doubts? basically we are almost completed the syllabus. Only 1 or 2% is remaining. So I would recommend you to read the entire CRE and come up with the questions. T reference has no effect. We cannot solve without considering T reference because it is technically not right. Because how enthalpy is defined is MCP delta T. But without solving T reference also we'll get the same answer. But T reference is the technically right way of solving the problem. RTD is for a reactor, not for order. RTD we're talking about a reactor. It doesn't matter whether you do which type of reaction there. So you will get exactly 1 kilowatt. If CPs are different, then T reference will not. Even if CPs are different, the value of, in the previous problem you see, A value is 50, B value is 100, C value is 150. If you see A plus B, you see, the nicely T reference will cancel on both sides. That is how the problem should be framed. If you are facing problem with RTD, one way is you have to hear the lecture again. Second thing is, if you still have time, then there are some YouTube lectures from IIT Bombay, Sanjay Mahajani. You can NPTEL course, if you try to see, there are 3-4 lectures on RTD. You can hear that lectures also. But better is you hear the class lectures again because you already heard once. Then I think second time hearing will improve the your understanding. So you can access the lectures, right? Class lectures. So I think we are, yeah, for our convenience, you can do it always, but don't write in front of anybody. That tells you that you have not understood delta H also. So I think no doubt. So I'm closing the session. So we'll meet tomorrow then. So RTD graphs explaining again will take a lot of time, no?